Spheres, cylinders, and cones. We know how to find the volume of these forms, but what if we had a more complex structure, such as this one, or maybe this one? How could we calculate the volume? You see, it wasn't until around the year 1612 that German mathematician Johannes Kepler discovered the solution to this problem. He found that we could mathematically calculate the volume of these circular forms through the concept of solid revolution. This branch of calculus allows us to determine the volume of a form that is created when a line segment is rotated around a fixed axis. Now, before we get into the math, let me show you exactly what I mean. Let's take a look at a sphere, or perhaps a basketball. This shape is essentially a semicircle that is rotated around an axis. The same goes for a cylinder or a pop can. In this case, the form can be constructed by rotating a two-dimensional rectangle around a horizontal axis to create a three-dimensional form. We already know simple formulas that already tell us the volume of these shapes. In fact, we can even derive these formulas from using this method. Let's take a look at the volume of a sphere, for example. We can imagine that it is made up of cross-sections along the x-axis. These cross-sections are infinitely thin disks, which allows us to create a model for this sphere. The radius of each disk is y, since y is the distance between the x-axis and the surface of the sphere. By knowing the formula of the area of a circle, which is essentially what these disks are, we can replace the radius with y. However, we want this to be in terms of the sphere's radius because it is kept constant, unlike the radius of the disks. To do this, we can simply set a triangle that expresses the relationship between x, y, and r. Using the Pythagorean's theorem, we can rearrange and isolate for y squared. Now, by plugging this new y squared value, we are able to create a new model of the area of each cross-section. Now, with the help of integration, we are able to find the volume of the sphere. To do this, we will integrate the area of the disk with respect to x, with the interval from -r to r. As you can see, this interval covers the whole horizontal shape of the sphere. We can start by taking pi out and isolating for 1/2 of the sphere by putting a 2 beside it. Next, we take the antiderivative and must evaluate for r. This is what we are left with, and now we must evaluate for 0, which returns 0. This leaves us with the derivation of the volume of a sphere that we all know and love. So, we know that these are the same, but why is this concept so important? Well, the solid of revolution is most useful when we have complex forms that do not follow the formulas on your cheat sheet. Forms that look like this. We can see these forms on legs of tables or types of cones. We can use the idea of solid revolution to divide this new 3D form into infinitely small disks and calculate the form that way, as we did with the sphere. These forms can be found everywhere. You just have to look around. And so the next time you eat a donut, remember that it is a 400-year-old concept that can determine how much of a doughy treat you're about to devour.